In this video, we're going to do some examples of using the method of partial fractions to evaluate some integrals. So let's start with example A. Example A will be the indefinite integral of, and we're using partial fractions, so we need a rational function. Remember that a rational function is a polynomial divided by a polynomial. So let's say x minus 4 in the numerator and x squared minus 5x plus 6 in the denominator, dx. So here we have a rational function. If we want to use partial fractions, you have to find the partial fractions expansion for the integrand. And in order to do that, the first thing to do is to factor the numerator and the denominator. The numerator doesn't need to be factored in this case. The denominator, however, can be factored, so we should do that. You always want to make sure that it's in reduced form. So we have x, 3, 2, and these both need to be negative. There we are. So we have two linear, remember linear means degree 1. We have two linear factors, and they're distinct, meaning they're not the same. So two factors in the denominator means two terms in the partial fractions expansion. The first one corresponds to the first factor, and the second one corresponds to the second factor. These are degree 1. The factors are degree 1. So the thing that goes in the numerator is 1 degree smaller, which is a constant. A constant is degree 0, which is 1 lower than a linear term, which is degree 1. So let's just write degree 1, and here it's degree 0. Okay, now in order to complete this problem, we need to figure out what a and b are. Once you have a and b, it's actually fairly easy to integrate these. The first one, if you integrate the first one, it's going to be a times the natural logarithm of the absolute value of x minus 3. The second one will be b times the natural logarithm of the absolute value of x minus 2. So once you actually have a and b, the actual integration is pretty straightforward, unlike the thing that you start with, and that's the whole reason we're doing the method of partial fractions. So let's figure out what a and b are. Now the way that you proceed is you need to add these two fractions together, give them a common denominator. So the first one has an a in the numerator and x minus 3 in the denominator. What it needs is an x minus 2. But if you put it in the denominator, you have to put it in the numerator first, or as well, rather. And then it's b over x minus 2. This one needs an x minus 3, but again, it needs to go in the numerator as well. So now they have a common denominator, which is x minus 3 times x minus 2. The numerator is a times x minus 2 plus b times x minus 3. And the denominator is x minus 3 times x minus 2. So now we have two fractions, two rational functions, which are equal, and they have the same denominator. So that means their numerators have to be equal as well. So this numerator is equal to that numerator. So that tells us that x minus 4 is equal to a times x minus 2 plus b times x minus 3. X minus 3. There we are. Now there's more than one way to solve for a and b. The way that I'm going to do it is I'm going to distribute this a, and then I'm going to distribute the b. The next thing I'm going to do is I'm going to group together the terms that have an x, and I'm going to group together the constants. Here's one, and there's another one. So on the left side we have x minus 4. On the right side we group up everything that has an x, a plus b times x, plus, and then we have minus 2a minus 3b, like that. So the constant term has to be equal on both sides. We have two polynomials here, and we're saying that they're equal to each other. The only way that can happen is if the constants are equal and also the linear terms are equal. Now, right there, there's a 1. We don't always write it in, but there's a 1 there. So what you have is that the linear term, which is 1, has to be equal to a plus b. So the linear term on the left is 1 and the linear term on the right is a plus b. Similarly, the constants have to both be equal. So the constant on the left is negative 4, and the constant on the right is minus 2a minus 3b. It's the thing in the parentheses there. Those are the constants. So now we have two equations and two unknowns, and what we want to do is we want to solve for a and b. Again, there are different ways to do this, but perhaps the easiest way is to solve one of them for a or b. Let's just solve it for b, and then you plug that into your other equation. So you have minus 4 equals minus 2a minus 3 times b, which is 1 minus a. So minus 4 is equal to minus 2a minus 3 plus 3a. Minus 4 is equal to 3a minus 2a is going to give you 1a minus 3. And then you just add 3 to both sides. And on the left, you're going to get minus 1, and on the right, you're just going to get a. So now you know what a is. And then you just take that and plug it back in there. So you're going to have b is equal to 1 minus minus 1, which of course is 2. So b is equal to 2. And that's your second value. That's the value of b. Okay, so that gives us a and b. So now we know that x minus 4 divided by x minus 3 times x minus 2 is equal to a is negative 1 over x minus 3 plus b is 2 over x minus 2. So if we're going to integrate the thing on the left, which is x minus 4 over, and the way we had originally written it, it was not factored, so it was x squared minus 5x plus 6 dx. This is equal to the integral of minus 1 over x minus 3 plus 2 over x minus 2 dx. And each one of these is going to give you a logarithm. So it's minus ln absolute value of x minus 3 plus 2 ln absolute value of x minus 2 plus a constant. And that's your answer. If you want, you can think of both of these as substitutions. So for the first one, you use the substitution u equals x minus 3. And for the second one, w equals x minus 2. So you have these two substitutions, and that's where our answer comes from. Let's just move it down a little bit. There we are. All right. So that's our first example. So let's do example B. For example B, we're going to integrate, and this will be a rational function again. So in our numerator, we'll have x squared minus 2x plus 1, and in the denominator, we'll have x to the 4th minus x squared dx. In order to use the method of partial fractions, you need to know what all of the factors are in your denominator. So it's important that you factor it. So let's do that here. X squared minus 2x plus 1, that's our numerator. And we want to factor the denominator, x to the 4th minus x to the 2. Well, the first thing you can do is you can factor out an x squared. That's going to leave you with x squared minus 1. And in the numerator, we haven't done anything yet. X squared minus 2x plus 1. Now the denominator has this x squared minus 1 term, and that is the difference of squares, so we can factor that again. So you're going to have x squared times x minus 1 times x plus 1. And in the numerator, let's not do anything yet, x squared minus 2x plus 1. In the bottom, we actually have 4 factors. It might look like 3 at first, but there's actually 4. X plus 1 is a factor, x minus 1 is a factor, and x squared is 2 factors. This is actually x times x, so there are actually 4 factors. However, we actually can factor the numerator as well. This function, this rational function, is not in reduced terms, because if we factor the numerator, that's going to be x minus 1 times x minus 1. It's x minus 1 squared. And in the denominator, we're going to have x squared times x minus 1 times x plus 1. So you can see it's not reduced. The x minus 1 in the numerator and the denominator can cancel. And we just have x minus 1 over x squared times x plus 1. So in order for the method of partial fractions to work properly, you need to make sure your rational function is in reduced form. So it is now. So we have x minus 1 over x squared times x plus 1. Okay. Now we have three factors. Remember, the x plus 1 is one factor, and the x squared is actually two factors. So since there are two factors, we're going to have, since there are three factors, we're going to have three terms in our partial fractions expansion. So the first one is x, then x squared, and then x plus 1. These are our three terms. The thing that goes in the numerator is 1 degree smaller than the factor that you started with. So here I have a factor of x, degree 1, so a constant goes on top. Here I have, it's an x squared, but the factor itself is x. It's just that x is repeated, x times x, but it's still a linear factor, which is degree 1. So that means a constant goes on top. And x plus 1 is degree 1, so that's just going to be a c. There we are. So this is our partial fractions expansion form. We just need to figure out what a, b, and c are. And the way we do it is the way that we did it before. You add them together by giving them a common denominator. So we have a over x. Now this one, it needs an x, but it also needs an x plus 1 in order to have a common denominator. And if you put it in the denominator, you have to put it in the numerator as well. Then plus b times x squared. It already has x squared. You don't need to multiply it by x because it's already got two of them. But you do need to multiply it by x plus 1. X plus 1. So you have to put that in the numerator as well. And then finally, plus c over x plus 1. And the thing that this is lacking, see, I want to make it look like my original denominator. My original denominator had x squared times x plus 1. The thing I'm missing is the x squared. There we are. Now the next thing to do is to combine them because they all have the same denominator now, so we can do that. They all have a common denominator. So the numerator is going to be a times x plus 1 plus b times x plus 1 plus c times x squared divided by x squared times x plus 1. Now again, you have two rational functions, two fractions which are equal, and they have the same denominators. So that means their numerators have to be the same. So x minus 1 is equal to all of that. So that tells us we have x minus 1 equal to ax times x plus 1 plus b times x plus 1 plus cx squared. So we need to find a, b, and c. And again, there are multiple ways to do this, but the way that I'm going to do it is just like last time. I'm going to group together everything that has x squared and x and so forth. So let's begin by distributing on the right. So ax times x is ax squared plus ax times 1 plus b times x plus b times 1 plus cx squared. So now I need to group together everything that has an x squared, everything that has just an x, and, well, there's only one constant, but we'll group together the one constant with itself. So on the left we have x minus 1. That's going to equal a plus c times x squared plus a plus b times x plus b. And now we have two polynomials which are equal to each other. So that means all of the coefficients have to be equal to each other. The constant terms have to be equal. So in particular, that means that b is equal to minus 1. The coefficient of x has to be equal. And again, it's the same thing. This is 1 times x. So the coefficients of x have to be equal. So if two polynomials are equal, then all of their coefficients have to be equal. So we're going to have 1 is equal to a plus b. Well, what about this term in front of the x squared? we don't have an x squared on the left. So you might think, what is it equal to? We can have an x squared term there if we want. It's just 0 times x squared. There's no x squared term. That means the coefficient is 0. So that means 0 is equal to a plus c. And now we're essentially done because we have that b is equal to minus 1 already. The second equation here tells us that 1 is equal to a plus b, but we know that b is equal to minus 1. So we have 1 is equal to a minus 1, so 2 is equal to a. And over here in this last equation, we have 0 is a plus c, so in other words, c is equal to negative a, but a is equal to 2, so c is equal to negative 2. And now we have our partial fractions expansion. So x minus 1 over x squared times x plus 1 is equal to a over x plus b, which is negative 1, over x squared plus c, which is a negative 2, over x plus 1. And the thing we wanted to integrate was equal to this. It wasn't written like that. It wasn't factored or reduced. So it's x squared minus 2x plus 1 divided by x to the fourth minus x squared. And we're integrating that with respect to x. So this is equal to the integral of, and now we have 2 over x minus 1 over x squared minus 2 over x plus 1 dx. And these terms we can integrate. So this is going to be 2 times ln of the absolute value of x. Now this one, you might be tempted to call that ln of x squared. That's not what it is. This term right here, this is x to the negative 2. So you have to use the power rule. So you increase the exponent by 1. Now there's already a minus sign here, so you bring down the minus sign, and what you're going to end up with is plus 1 over x. And then minus 2 times ln of x plus 1. Plus a constant of integration, and that's your answer. Now let's just go back over this just for a second, or at least one part of it. Let's look at our partial fractions expansion that we have up here. Let me just copy and paste it so that we can look at it. Copy, paste. Let me get rid of these extra lines. So remark, the partial fractions expansion has this form. You might look at that and think, well, how come we're using this x and x squared here? Because this has an x squared. You might think, well, since that's quadratic, shouldn't we use one quadratic term in the denominator and a degree 1 polynomial above it? So can we use something like x squared plus something over x plus 1, where here we're treating this not as a repeated linear factor, but instead we're treating it as a quadratic. And if you treat that as a quadratic, you'd have to put a polynomial of degree 1 in the numerator, ax plus b. Can we do that? And then this would still be c. So we have a quadratic in the denominator, and so in the numerator we let ax plus b be our polynomial with unknown or undetermined coefficients, because the idea is the numerator has to be 1 degree smaller than the denominator. And that's what it looks like here, because we have a degree 2 in the denominator and a degree 1 in the numerator. Degree 1. Treating this as degree 2. So this is actually the same thing. Why is it the same thing? Because if you have ax plus b over x squared, that's the same thing as ax over x squared plus b over x squared. And here, that x will cancel with one of those. And what do you end up with? You end up with a over x plus b over x squared. And that is exactly what we had before. Let's put it in blue so it stands out. So you see it's actually the same thing if you treat the denominator like a degree 2 polynomial. But there's a very good reason why we don't do this. The objective is to integrate, and it's not easier to integrate that than it is the thing that we started with, ax plus b over x squared. You have to reduce it to this form in order to be able to integrate it anyway. So you might as well just start with that to begin with, instead of looking at this term and then splitting it up afterwards in this way. Okay, but the point is, you can do it, it's just there's no need to, because you need to be able to integrate the result. This thing you can't integrate, but that thing you can. Let's do another example. So this would be example C. And again, we want to integrate a rational function, so it's going to be some sort of fraction with respect to x. Let's try some cases where we have irreducible quadratic polynomials. So on the bottom, let's say x squared plus 1 and x squared plus 4. Those are both irreducible quadratics. In the numerator, let's keep it simple. Let's just say x squared plus x, for example. We've already factored the bottom there just to make it a little bit easier for us in the interest of time. All right, so we want to evaluate this integral, and like the other ones we've seen, we don't necessarily know how to do it as it is, but what we can do is we can write it out in its partial fractions expansion, and we'll be able to integrate those pieces. There might be a little bit of a twist to it, as we'll see as we go along, but let's start by looking at the partial fractions expansion. So in this case, we have two factors in the denominator. So if you have two factors, that's going to lead to two terms in the partial fractions expansion. So this is the partial fractions expansion, of course. Or at least this is the form of it. The first factor, x squared plus 1, gives us our first term, and the second factor, x squared plus 4, gives us our second term. We don't know exactly what's in the numerator, but it's going to be 1 degree smaller than the quadratic below it. So we're going to have ax plus b, and over here we'll have cx plus d. Now you might be tempted to write ax plus b here, but don't do that because we've already used a and b. You're not allowed to reuse the letters. Okay, so what do? Well, we do what we always do. We give them a common denominator. So the first one has x squared plus 1, ax plus b in the numerator. We want it to look like the denominator of the term we've started with. That's the idea. You're giving them a common denominator and adding them together so you get back what you started. It has an x squared plus 1. What it needs is an x squared plus 4. So you put it in the denominator but also in the numerator, because really you're multiplying by 1. Then we have cx plus d over x squared plus 4, and this one needs an x squared plus 1, but you need it in the numerator as well. Okay, now what do? We multiply along the bottom to get the common denominator. You don't need to expand that. We just leave it as it is. But we can now combine these two fractions into one. The first one has ax plus b times x squared plus 4 plus cx plus d times x squared plus 1. And all of this is over the common denominator, x squared plus 1 times x squared plus 4. So now we need to figure out what all of these a, b's, and c's and d's are, but we can do that. We have two rational functions, two fractions, that are equal. They're equal to each other, and they have the same denominators. So that means they must have equal numerators as well. So we write it down. X squared plus x is equal to ax plus b times x squared plus 4 plus cx plus d times x squared plus 1, like so. Now, we have two polynomials, and if you have two polynomials that are the same, then their coefficients must be the same. We can't see the coefficients on the right here yet. Let's expand it. So on the left we have x squared plus x. This is equal to ax times x squared is x cubed, plus ax times 4 is going to give us 4ax, plus b times x squared is bx squared, plus b times 4 is 4b. So that's just the first term there, the first product. And now we're going to have the same sort of thing for the second product. Now I'm not going to have enough room here, so let's put it slightly below. Plus cx times x squared is going to give us cx cubed, plus cx times 1 plus dx squared plus d times 1 is just going to give you a d. Okay, so just like before, we want to collect the like terms. So you have a cube here and here. So that's going to be a plus c times x cubed. There's a square, there's another square. So it's b plus d x squared. Plus, here's a linear term, there's another one, 4a plus c times x. And now we gather together the constant terms, 4b plus d. On the left, we have x squared plus x. If you like, you can write a 1 in front of those. 1x squared plus 1x. Because we're equating the coefficients, it might help if you actually see what the coefficients are. Now what you might notice is that there is a constant term here, but there doesn't appear to be one on the left side, but there is, it's just 0. 0 is the constant. Also, there's an x cubed term here, but you don't see one on the left side. That's because it's 0x cubed. You don't need to write in the 0 terms, but sometimes it helps because you can actually then see what the coefficients are, because what we want to do is equate the coefficients. And we can see, for example, that there are cubic terms. So the coefficient for x cubed is a plus c, but that has to be equal to 0. So you have 0 equals a plus c. Then you have the square terms, and those correspond to the coefficient of the square term, which is 1. So you have 1 equals b plus d. Then you have the linear terms, which are degree 1, and those two are equal to each other as well. So the linear term on the right, or I should say the coefficient of the degree 1 term, the linear term on the right, is equal to the coefficient of the linear term or degree 1 term on the left. So we have 1 is equal to 4a plus c. And finally, the constants are equal. Well, on the right, the constant is 4b plus d, but on the left, the constant is 0. We're left with 4 equations and 4 unknowns, which might seem daunting, but the presence of all of these zeros here, well, those two zeros, makes things a little bit easier. So we can start on the left and we can solve for c, for example. c is equal to negative a. And notice that there's a c and an a term in the third equation. So we can plug in that a there and we get 1 equals 4 times a, which is a negative c. Actually, we wanted to plug in not into the a, we wanted to plug into the c. So we'll plug it in there. So it's 4a plus c, which is negative a. So not that it matters, we could have solved for a equals negative c and done the same thing. But we end up with 4 equals 3a, or a is equal to 1/3. So that's the first one. And that immediately tells you what c is, because c is the opposite of a, so it's negative 1/3. There we go. Well, now we can do the same thing with b and d. The remaining two equations both have b and d, so that makes things a little bit easier too. They came in pairs. So if you start on the rightmost equation, you can solve for d. D equals minus 4b. I'm just solving for d instead of b, because if you solve for b, you end up with minus 1/4. Not that that's a problem, but it's usually easier if you have the 4 in the numerator instead of the denominator. So now we're going to plug that, d, into the equation that's number 2, and that's going to give us 1 equals b plus d, which is negative 4b. So we have 1 equals negative 3b. So b is equal to negative 1/3. So lots of 1/3s here. And notice that d, now we can plug this back into here, and d is equal to minus 4 times b, which is a negative 1/3. So d is equal to positive 4/3. There we are. So now we have c, b, a, and d. And now we can plug these back into our original partial fractions expansion, which is just up here. So we had that x squared plus x over x squared plus 1 times x squared plus 4 is equal to ax plus b, so that's 1/3 x plus a negative 1/3 divided by x squared plus 1 plus, and now it's c minus 1/3 x plus d over x squared plus 4. If we want to integrate the thing on the left, which we do, we can actually integrate the thing on the right. Now, that might not seem like it's even anything better, because how are you supposed to integrate those? Well, as they are, it's a little bit troubling. However, you can break these apart into separate fractions. So this is a 1/3 times x over x squared plus 1 minus 1/3 times 1 over x squared plus 1. So that is what you get when you break up the first term into its two pieces. You can do the same thing with the next term. So you can write that as minus 1/3 x over x squared plus 4, and then it's plus 4/3 times 1 over x squared plus 4. Now, we have, instead of two terms, we have 4. So let's see. The second term becomes this pair here. So the first one breaks apart into these two, and the second one breaks apart into those two. So now we have a total of 4. But what's great about this, we can integrate all of these. Now, you might have to do some substitution along the way, like right there, you'll have to do substitution. This one is not so bad. That's an arctangent. That's an arctangent of x, or at least the antiderivative is arctangent of x. Okay, so let's do this now. Let's integrate. So the integral of x squared plus x over x squared plus 1 times x squared plus 4 dx is going to be the integral of all of that, but let's do each one individually. So it's going to be equal to 1/3 times the integral of x over x squared plus 1 dx minus 1/3 times the integral of 1 over x squared plus 1 dx minus 1/3 integral x over x squared plus 4 dx plus 4/3 times the integral of 1 over x squared plus 4 dx. Okay, so it didn't have quite enough room there, but let's just move it over to the left again, just a little bit. And maybe we'll just fix that dx. There we are. Now, each one of these we can do individually. So for the first one here, or just the integral, you want to use the substitution. Let u be equal to x squared plus 1, then du is equal to 2x dx. So we have an x dx, you just need a 2 in front. So you put a 1/2 in front of that. And so now this one is 1/6 times 1 over u. This thing is 1 over u du, so that's going to be ln of the absolute value of x squared plus 1. you don't actually need the absolute values there because x squared plus 1 is always positive. X squared plus 1 is always greater than or equal to 1. So you don't actually need the absolute values there. This second one, that one has an elementary antiderivative. This is just arctangent of x. So you have minus 1/3 arctangent of x. The next one is similar to the first. Here, again, you use a substitution. We've already used u, so let's use w. X squared plus 4. Then dw is 2x dx. And again, you just need a 2 there, and that's your dw, just like this is your du over here. And then you're left with 1 over u. Well, we have to put the 1/2 in front as well. So this is minus 1/6, and this again is 1 over w dw. So it's ln absolute value of x squared plus 4. And again, you don't need the absolute values there because x squared plus 4 is greater than or equal to 4, so it's certainly always positive. Now what about this last one? Well, the last one is also a substitution. Notice it looks a lot like the one that gave us arctangent, and it will give us some type of arctangent, but it's not going to be just arctangent of x. There's going to be a 4 in there somewhere. So let's actually just write this one out. Let's write it in a different color. So the integral 1 over x squared plus 4 dx. How do you go about doing a problem like this? Well, the idea is you want to make it look like 1 over x squared plus 1. So what I'm going to do is I'm going to factor out the 4. So this is the integral of 1 over, and I'm going to factor out the 4, and that's going to leave me with x squared over 4 plus 1 dx. So then I can take that 1/4 out, and so what we'll have then is 1 over 4 times the integral of 1 over, and we're going to have x squared over 4, but let me write that as x over 2 quantity squared du, not du, dx. And so now I need to use a substitution. So we've already used u and w, might as well use v now. So let's let v be equal to x over 2, and then dv is 1/2 dx. So what have we got? We've got a 1/4 times the integral of 1 over x over 2 quantity squared plus 1 times dx. We need a 1/2 there, so you have to multiply by 2 instead of dividing like we usually do. And now we have 2 over 4, which is 1/2, times the integral of 1 over v squared plus 1 dv. And now this is arctangent of v. So this is 1/2 arctangent of v plus a constant. But remember what v was. It's x over 2. So we didn't actually have a 4 anywhere. We just had a bunch of 2's. So now we can take this and plug it right back into our integral up there. And so what are we going to end up with? We're going to end up with plus 1/2 arctangent x over 2 plus c. And that's our answer. Let's do just one more example. So this will be example D. The integral of x squared over x plus 1 dx. Now, this is unlike any that we've done so far because this is not proper. This is not a proper rational function. The degree on top is bigger than the degree on the bottom. See, this is degree 2. And the bottom is just degree 1. So that means we can't use the method that we've been describing, the method of partial fractions, at least not right away. When you have a situation like this, the first thing you do, first step, is to write it as a polynomial plus a proper rational function. Now, how do you do that? Well, there are a couple of ways to do it, but basically you use polynomial division. Use polynomial division. Once you do that, you can integrate the polynomial part easily, just using the power rule over and over again repeatedly. And then the proper rational function, this one, well, so the polynomial you can integrate as you usually do. So integrate using power rule repeatedly. And then the proper rational function, you can use partial fractions for that. It won't actually require partial fractions for this one because there's only one factor in the denominator. If there were multiple factors, then you might have to use partial fractions. Let's go ahead and see how this works. So we're dividing x plus 1 into x squared. So we have to use polynomial division. What do you multiply x plus 1 by to get x squared? Well, you have to multiply an x, because x times x is going to give you x squared. But if you do that, you also have this x times 1 part, so that's going to be plus x. So x times x plus 1 is x squared plus x. And now you have to see what the remainder is for that. And the x squareds cancel and you just end up with a minus x minus x. So now, how do you get a minus x out of x plus 1? Well, of course, you multiply it by minus 1. So minus 1 times x plus 1 is going to be a minus x minus 1. And then you have to look at the remainder. Let me just move this up slightly so it's on the same page. So now we again look at the remainder, and you get minus x minus a minus x, or minus x plus x, is 0, and then you get minus a minus 1 is plus 1, and that's your remainder. So plus 1 over x plus 1. And that is, or rather, that is the result. So x squared over x plus 1 is equal to x minus 1 plus 1 over x plus 1. And this is something that we can integrate, or rather all of these three terms are things that you can integrate. Notice that here there's a polynomial, and here you have a proper rational function. And all of these things you can integrate. So the integral of x squared over x plus 1 dx is equal to the integral of x minus 1 plus 1 over x plus 1 dx, which is x squared over 2 minus x plus the natural logarithm of the absolute value of x plus 1. There we are. Oh, and plus a constant of integration, of course. And that's your answer. If you don't want to use polynomial division, there are usually other ways you can do it, little algebraic manipulations. So, for example, if we start with x squared over x plus 1, suppose I want to reduce this to the form that we see here without using polynomial division. Well, the idea is I need x plus 1 to divide into it. So the way to do that is to start with this x squared over x plus 1. And what you want to do is you want to add in an x to it. Now, the idea is that if I factor out an x, I'm going to be left with an x plus 1. Of course, you can't just add in an x. You also have to subtract an x. So that gives you x squared plus x minus x over x plus 1. And why would you do a thing like that? Well, if you factor out the x from the first two terms, you have x times x plus 1 over x plus 1 minus x over x plus 1. The x plus 1's cancel, and you're left with x minus x over x plus 1. This shouldn't be a surprise, because if you go up a little bit, that's exactly what we have here, x. And notice that we had an x squared plus x here, and what we were left over with was a negative x. And that's that negative x right there. So now we do the same thing to this one. We add 1 and subtract 1. So that gives you x minus x plus 1 minus 1 over x plus 1 equals x minus x plus 1 over x plus 1, and then minus 1 over x plus 1, like that. Now these two cancel out. That's just going to be a 1. So then you have x minus 1 minus a minus is plus 1 over x plus 1. And that's exactly the same thing. X minus 1 plus 1 over x plus 1. It's exactly the same. So that's another way to do polynomial division without explicitly doing polynomial division. Either one is fine.